September 27, 1942. 0614 hours. Richmond Shipyard No. 2, California. A single-engine Stearman biplane descended through morning fog, its pilot executing what observers called the most dangerous stunt in American industry. What Henry Kaiser's engineers had deemed impossible, welding a ship's hull in the correct sequence while simultaneously managing 17 separate construction zones, was about to be solved by a bush pilot from Alaska who had never built anything larger than a dog sled. The man in that biplane, Robert Dusty Patterson, would transform American shipbuilding from a craft into a science, and in doing so, would make Adolf Hitler's U-boat campaign irrelevant. Before Patterson's aerial choreography, Liberty ships took an average of 244 days to build. After his system was implemented, Kaiser's yards would launch a complete 10,000-ton freighter every 96 hours. The British Admiralty called it impossible. The Germans called it American industrial magic. Patterson called it just flying in circles and watching where the stupid mistakes happen. The mathematics of defeat had been calculated in a windowless room at the British Admiralty in January 1942. Commander Roger Winthrop, chief of the Anti-Submarine Warfare Division, had presented figures that predicted Britain's starvation by autumn. German U-boats were sinking merchant vessels at a rate of 4.3 ships per day. British and American shipyards combined were producing replacements at 1.1 ships per day. The equation was simple and fatal. President Roosevelt had responded with characteristic optimism, announcing a program to build 2,751 standardized cargo vessels, Liberty ships, using revolutionary mass production techniques. The contract went to Henry Kaiser, an industrialist who had never built a ship in his life but had constructed the Hoover Dam in 4 years. Kaiser promised miracles. He delivered chaos. By September 1942, Kaiser's Richmond Shipyard No. 2 employed 23,000 workers operating around the clock in 3 shifts. The shipyard sprawled across 150 acres of reclaimed marshland on San Francisco Bay. 7 building ways stretched parallel to the water, each capable of supporting the construction of a 441-foot vessel. The facility consumed enough electricity to power a city of 50,000. Steel arrived by train at a rate of 2,000 tons per day. Welding rod consumption exceeded 10 tons daily. Yet despite these massive inputs, production had stalled at an average of 1 ship every 18 days, far below the rate needed to offset U-boat sinking. The problem wasn't equipment or manpower. Kaiser had recruited the best naval architects from East Coast yards. He had installed the most modern welding equipment available. He had workers eager to prove themselves in an industry that had previously excluded them, women, African Americans, workers over 50 whom traditional yards considered too old. The problem was coordination. A Liberty ship required 250,000 separate parts assembled in precise sequence. The hull alone demanded 30,000 individual welds performed in specific order to prevent stress fractures. 17 separate construction zones, bow section, stern section, engine room, 5 cargo holds, deck structures, and superstructure, all had to progress in synchronized harmony. Traditional shipbuilding had relied on master builders who carried construction sequences in their heads, accumulated through decades of apprenticeship. Kaiser's yards had no such masters. The engineering solution seemed obvious: create detailed construction schedules showing every task in sequence. Kaiser's planning department produced documents covering entire warehouse walls. Critical path charts mapped 10,000 individual tasks with dependency relationships connecting them like a spider web. The schedules were mathematically perfect and completely useless. The problem was visibility. Foremen couldn't see their schedules while working inside hull sections. Welders couldn't consult charts while balanced on scaffolding 40 feet above the deck. Crane operators couldn't reference task lists while maneuvering 5-ton plates through narrow clearances. The disconnect between planning and execution created cascading delays. A single missed sequence, installing electrical conduit before structural frames, for instance, could require demolishing and rebuilding entire sections. By late September, Kaiser faced a crisis that threatened the entire Liberty ship program. production rates were declining as confusion increased. Worker morale was collapsing as their efforts resulted in costly rework rather than finished ships. The British Admiralty was preparing contingency plans for evacuating the government to Canada when Britain's food supplies ran out. Robert Patterson hadn't intended to revolutionize shipbuilding. The 34-year-old bush pilot from Fairbanks had come to Richmond looking for steady employment after the military rejected him for color blindness. His wife, Eleanor, was expecting their third child, and flying supply runs to Alaskan mining camps didn't provide the security of shipyard wages. Patterson had applied for a position as a welding inspector, a job that didn't require distinguishing red from green. The shipyard personnel office had other ideas. Patterson's application mentioned 4,200 logged flight hours, including extensive experience in aerial surveying for Alaskan Territorial Survey. The yard safety director, Thomas Brennan, saw an opportunity. Richmond Shipyard had recently acquired 2 Stearman biplanes for executive transport and emergency medical evacuation. Brennan needed someone to maintain flight readiness and occasionally transport Kaiser executives to meetings in Los Angeles or Seattle. Patterson accepted immediately. The pay was double what welding inspectors earned. Patterson's first flight over the shipyard occurred on September 15, 1942, a routine test flight after engine maintenance. Banking over the construction ways at 800 feet altitude, Patterson observed something that yard supervisors walking among the steel couldn't see: patterns of inefficiency visible only from above. He watched crane operators in adjacent bays lifting identical components within minutes of each other, their movements uncoordinated despite serving the same construction phase. He observed materials stockpiled at the wrong end of building ways, requiring internal transportation that clogged movement corridors. He saw welding crews standing idle in one section while 3 crews competed for space in another, their work lights visible as bright clusters from his cockpit. Most significantly, Patterson observed something that would become the foundation of his system: construction zones that had fallen behind schedule became visible bottlenecks, their delayed status apparent from the missing structural elements that should have been present at that stage. From ground level, a foreman might not realize his section was 3 days behind schedule. From 800 feet, Patterson could see that the frames that should have been vertical were still horizontal on staging pallets. That evening, Patterson sketched what he had seen on his navigation plotting board. He marked each building way with construction phase indicators, color-coded by progress status. He drew movement patterns for cranes and materials, identifying conflicts and suggesting alternatives. The sketches covered 6 pages of his flight log. Patterson showed his drawings to Brennan the following morning. Brennan, a former Army Corps of Engineers officer, immediately recognized their value. He arranged a meeting with Albert Bechtel, Kaiser's production superintendent. Bechtel, exhausted from managing yet another day of cascading delays, barely glanced at Patterson's sketches. "Son, I've got 40 foremen down there who can't figure out how to build these ships. You think doodling from an airplane is going to help?" Patterson's response would become legendary in Kaiser's organization. "Mr. Bechtel, your foremen are trying to build ships while standing inside them. That's like trying to see the forest when you're a tree. Let me show you what your shipyard looks like when you're not a tree." Bechtel agreed to a demonstration flight the following morning. What he saw from Patterson's cockpit would change American industrial production forever. September 18, 1942, 0630 hours. Patterson took Bechtel up in the Stearman for what was scheduled as a 15-minute overview flight. They stayed aloft for 90 minutes. Bechtel filled an entire notepad with observations, his engineer's mind immediately grasping what Patterson's pilot's perspective revealed. From 800 feet, the shipyard transformed from chaos into readable patterns. Bechtel could see that building way 3 was progressing faster than adjacent ways because its crane operator had developed an efficient movement pattern, retrieving materials from the stockpile, delivering them to the installation point, then collecting scrap for disposal on the return path, a continuous loop that minimized empty movements. Meanwhile, cranes on other ways were making separate trips for each task, tripling their operational time. More critically, Bechtel observed that construction delays cascaded in predictable patterns. When the bow section fell behind schedule, it created a bottleneck that delayed frame installation, which delayed deck plating, which delayed superstructure assembly. From ground level, each delay seemed independent. From above, they were clearly linked in chains of causation visible only when viewed as a whole. Patterson proposed a radical solution: conduct aerial surveys 3 times daily, dawn, noon, and dusk, photographing each building way from consistent altitudes and angles. Use these photographs to track construction progress against planned schedules. More importantly, use them to identify and correct bottlenecks before they cascaded into major delays. Bechtel saw the potential but also the problem. "Bob, I've got 17 construction zones per ship, 7 ships under construction simultaneously. That's 119 separate work areas. How are you going to photograph all of them meaningfully, 3 times a day, and get that information to foreman fast enough to matter?" Patterson had already worked out the solution during his solo flights. The Stearman's cruising speed of 95 miles per hour meant he could circle the entire shipyard in 8 minutes. Mounting a camera facing straight down, what aerial surveyors called a vertical shot, he could photograph all 7 building ways in a single pass. A second pass at a different angle would capture detail shots of specific problem areas. The real innovation was Patterson's proposal for information distribution. Rather than developing photographs and distributing prints, a process taking hours, Patterson suggested marking construction status directly on a master board using colored pins. Green for on schedule, yellow for minor delays, red for critical bottlenecks. The board would be mounted in the main planning office where all shift supervisors gathered before each shift change. More radically, Patterson proposed flying his surveys during shift changes themselves, 0600, 1400, and 2200 hours, when supervisors were briefing incoming crews. This meant Patterson would be conducting surveys in darkness for the night shift changes. He would be flying a fabric-covered biplane over an industrial area filled with cranes, smokestacks, and construction equipment, in the dark, 3 times per night. Bechtel asked the obvious question. "Bob, you'll kill yourself." Patterson's response revealed the Alaska bush pilot's relationship with calculated risk. "Mr. Bechtel, I've flown supply drops to mining camps in Arctic whiteouts where I couldn't tell the ground from the sky. I've landed on glaciers by feeling for the surface with my wheels. Your shipyard's got lights, it's got landmarks, and it's not trying to kill me with weather. This is the easiest flying I'll ever do." Bechtel authorized a 1-week trial beginning September 21, 1942. Before we jump back in, tell us where you're tuning in from, and if this story touches you, make sure you're subscribed, because tomorrow, I've saved something extra special for you. September 21, 1942, 0558 hours. Patterson climbed into the Stearman's cockpit as the day shift gathered for morning briefing. The aircraft carried modifications completed overnight by the shipyard's machine shop, a Fairchild K-20 aerial camera mounted in a frame beneath the fuselage, pointed straight down, and a series of flare markers Patterson could drop to indicate critical problem areas to ground supervisors. The morning survey flight revealed what Patterson had suspected: construction bottlenecks were predictable and preventable. Building Way 5 showed frames installed out of sequence, a mistake invisible from ground level but obvious from above where Patterson could see the irregular spacing pattern. Building Way 2 had materials staged on the wrong side of the hull, forcing crane operators to make dangerous lifts over occupied work areas instead of over empty deck space. Patterson landed at 0614 hours, 16 minutes after takeoff. He rushed to the planning office where shift supervisors were still conducting briefings. Using a large-scale shipyard diagram mounted on the wall, Patterson placed colored pins at problem locations. Red pin on Building Way 5, frame sequence error, requires immediate correction before deck plating begins. Yellow pin on Building Way 2, materials staging inefficient, recommend repositioning before noon shift. Thomas Brennan, who had been skeptical despite authorizing the trial, watched the morning shift supervisors' reactions. Instead of defensive resistance, they showed immediate recognition. The Way 5 supervisor, James Hutchinson, actually slapped his forehead. That's why the deck measurements weren't matching specifications. We installed frame 42 before frame 41. From down there, they looked identical. The correction took 2 hours instead of the 2 days it would have required after deck plating had been installed over the misaligned frames. Patterson's first survey had prevented a mistake that would have cost $14,000 in materials and labor, more than Patterson's annual salary. But the real transformation came from Patterson's noon survey at 1,358 hours. Flying over Building WWII, he observed something remarkable. The morning shift had been exceptionally productive, installing frames at nearly twice the normal rate. Patterson circled lower, trying to understand what made this crew different. Then he saw it. The WWII crane operator, a woman named Dorothy Fletcher who had transferred from a Sacramento cannery, had developed a rhythm that synchronized with the welding crews below. She wasn't just moving materials, she was anticipating the welder's needs, positioning the next frame before they finished the current one, eliminating the 5 to 10 minute gaps that occurred on other ways while welders waited for materials. Patterson dropped a green flare over Building WWII, his signal for exemplary performance. When he landed and briefed the afternoon shift supervisors, he didn't just report problems. He reported success. Whatever Fletcher's doing on WWII, we need her teaching every crane operator in this yard. Albert Bechtel, attending the noon briefing personally to evaluate Patterson's system, made an immediate decision. Dorothy Fletcher was promoted to lead crane operator trainer, with authority to standardize procedures across all 7 building ways. Her technique, invisible from ground level but obvious from 800 feet, would be studied, documented, and replicated. By September 23, just 3 days into Patterson's trial, Richmond Shipyard No. 2 was operating differently. Supervisors arrived at shift briefings expecting Patterson's aerial intelligence. They had begun calling his colored pins Patterson's traffic lights, green for good, yellow for caution, red for stop and fix immediately. The shipyard's error rate dropped by 40% in the first week. More significantly, construction time per ship began declining. Building WWII completed hull assembly in 14 days instead of the previous 18. Building WWII, which had been lagging behind schedule, caught up by correcting material staging problems Patterson identified from above. October 1942 marked the transformation from experimental program to systematic operation. Patterson's aerial surveys evolved from simple observation to active coordination. He began carrying a radio transmitter, allowing real-time communication with ground supervisors during flights. The steerman became a flying command post, directing shipyard operations with a perspective no ground-based manager could achieve. Patterson developed a standardized survey pattern that he could fly in exactly 12 minutes, covering all 7 building ways twice, once for wide-angle overview shots, once for detailed close-up photography of specific construction zones. He flew this pattern 9 times daily, 3 scheduled surveys at shift changes, plus 6 additional flights timed to critical construction phases when coordination was most essential. The aerial photography revealed patterns that revolutionized Kaiser's entire production philosophy. Patterson discovered that construction delays followed a predictable rhythm. Monday morning shifts were consistently slower, as workers reoriented themselves after weekend breaks. Thursday afternoon shifts showed peak efficiency, as crews hit optimal rhythm. Friday late shifts showed declining quality as fatigue set in. More importantly, Patterson identified what he called cascade points, specific construction phases where mistakes propagated through subsequent work. Installing the engine bed mounts was a cascade point. Errors here would affect shaft alignment, which would affect propeller installation, which would affect sea trials. Patterson began scheduling his flights to observe these critical phases personally, providing immediate feedback to prevent cascade failures. The system's effectiveness was proven during the construction of Hull 440, which would become the SS Robert E. Peary. On October 8, 1942, Patterson observed from above that the bow section assembly was progressing unusually quickly. He radioed Albert Bechtel directly, "WWII 4 is running fast. If we pull resources from WWII 6, which is ahead of schedule, and concentrate on completing 4's hull by end of shift, we could start launching preparation tomorrow instead of next week." Bechtel made the call. 200 workers from Building WWII moved to WWII for the final 8 hours of their shift. Patterson flew continuous observation, coordinating the massive resource reallocation from above. He directed crane movements to prevent conflicts, identified material shortages before they became delays, and spotted quality issues immediately. Hull 440's assembly was completed in record time, 8 days from keel laying to launch preparation. When the SS Robert E. Peary slid into San Francisco Bay on November 12, 1942, she represented something unprecedented, a complete 10,000-ton Liberty ship constructed in just 4 days and 15 hours from keel to launch. The achievement made international headlines. British newspapers called it impossible. German intelligence reports to the Kriegsmarine dismissed it as propaganda. Joseph Stalin sent a personal telegram to Roosevelt asking if the reports were accurate. They were. Patterson's aerial coordination had transformed shipbuilding from sequential construction, completing each phase before beginning the next, to parallel construction, where multiple phases progressed simultaneously under coordinated oversight. The technique was only possible because Patterson could see the entire construction process as a single system rather than isolated tasks. But Patterson had identified something even more significant during his flights. He had been tracking not just ship construction, but worker movements and efficiency patterns. What he discovered would prove as revolutionary as the aerial surveys themselves. Patterson's flight logs from November 1942 contained observations that had nothing to do with steel or welding. He had been watching people. From 800 feet, individual workers were tiny figures, but their collective patterns were clearly visible. Patterson observed that work crews didn't just build ships, they formed social networks that affected productivity in measurable ways. He noticed that certain workers became focal points where other workers gathered. These individuals weren't always the official supervisors. Patterson began marking these gravity wells, his term for workers who attracted others, on his survey maps. He recommended that Bechtel investigate whether these individuals possessed specific skills or knowledge that made them valuable informal leaders. Bechtel's interviews revealed something unexpected. The gravity wells Patterson identified were typically workers who had served longest in their current positions, not necessarily the most skilled, but the most experienced with the specific quirks of Richmond Shipyard's equipment and procedures. A welder named Vincent Romano knew that the power supply to Building WWII's southern section was slightly under voltage, requiring adjusted arc settings. A rigger named Louise Hamilton knew that the crane on WWII had a tendency to drift leftward during high lifts, requiring compensation. This institutional knowledge had been invisible to management but obvious to Patterson from above. Workers clustered around these experienced individuals not for social reasons but for survival, learning the unwritten rules that made their jobs possible. Patterson recommended that Kaiser formalize this informal knowledge transfer. Instead of random crew assignments, he suggested creating stable teams that kept experienced workers paired with newcomers. The results were dramatic. Construction quality improved as fewer mistakes were made. Training time for new workers decreased from 3 weeks to 10 days. Most significantly, worker morale improved measurably. Exit interviews with departing workers, which had previously cited too much confusion as the primary reason for leaving, now reported feeling supported and competent. Patterson's most controversial observation came in December 1942. Flying over the shipyard during an evening shift change, he noticed that workers from Building WWII consistently left the yard 10 to 15 minutes later than workers from other ways. Investigation revealed that WWII's location at the far end of the shipyard meant workers faced a longer walk to the exit gates. Those 15 minutes, multiplied by 800 workers per shift, represented 200 man-hours lost daily. Patterson proposed relocating the main entrance gate closer to the distant building ways. The shipyard construction office calculated the gate relocation would cost $8,000, a significant expense. But Patterson's aerial surveys had documented that the time savings would pay for the gate relocation in 11 days through improved productivity. The new gate opened on December 28, 1942. Within a week, production metrics confirmed Patterson's analysis. Building WWII-7's productivity increased by 6% simply because workers arrived at their stations less fatigued and departed without rushing to catch transportation home. By January 1943, Patterson's aerial survey system had expanded beyond Richmond Shipyard No. 2. Kaiser's other yards, Richmond No. 1, Richmond No. 3, and the Swan Island facility in Portland, all received their own survey aircraft and pilot coordinators trained by Patterson personally. The revolution had scaled. Preparing and narrating this story took us a lot of time, so if you are enjoying it, subscribe to our channel, it means a lot to us. Now back to the story. By March 1943, Patterson's aerial coordination system had transformed American shipbuilding capacity beyond anyone's predictions. Richmond Shipyard No. 2 was now completing Liberty ships at an average rate of 1 every 5.2 days. Kaiser's entire West Coast operation, for major yards, was producing finished vessels at a combined rate exceeding 1 ship per day. The impossible mathematics that Commander Winthrop had calculated in January 1942 had been reversed. American shipyards were now building ships faster than German U-boats could sink them. The statistical revolution was documented in War Production Board reports that tracked construction time per vessel across all American shipyards. In January 1942, the average Liberty ship required 244 days from keel laying to delivery. By March 1943, Kaiser's yards averaged 42 days. The best-performing yard, Richmond No. 2, where Patterson's system was most refined, averaged 27 days. Individual ships built during concentrated campaigns achieved even more remarkable times. The impact extended far beyond the hulls themselves. Patterson's aerial survey techniques had revealed inefficiencies in every aspect of shipyard operations. Material delivery schedules were restructured based on his observations of stockpile usage patterns. Worker shift assignments were optimized using data from his documentation of crew productivity rhythms. Even the shipyard cafeteria locations were relocated after Patterson noted that workers from distant building ways were losing 20 minutes per shift walking to lunch. Admiral Emory Land, chairman of the United States Maritime Commission, visited Richmond Shipyard on March 15, 1943. Patterson took him up for a survey flight. Land, a career naval officer who had overseen naval aviation development in the 1920s, immediately grasped what Patterson had created. "Son, you've turned shipbuilding into a ballet. Every worker, every crane, every material delivery, they're all dancing to music only you can hear from up here." Land's report to President Roosevelt emphasized that Patterson's innovation represented something beyond mere efficiency improvement. It demonstrated a fundamentally new approach to industrial coordination, using aerial observation to transform complex manufacturing from a series of isolated tasks into a synchronized system. Roosevelt ordered the War Production Board to study Patterson's methods for application to other critical manufacturing operations including aircraft production and tank assembly. The British Admiralty sent a technical assessment team to Richmond in April 1943. Their report, declassified in 1973, expressed astonishment at what Patterson had achieved. "The Americans have solved the construction coordination problem that has plagued shipbuilding for centuries. A single pilot in an obsolete biplane provides better construction oversight than our entire quality control bureaucracy. This represents a revolution in industrial management that extends far beyond shipbuilding applications." German naval intelligence reports from mid-1943, captured after the war, reveal that Kriegsmarine analysts initially refused to believe American production figures. When reconnaissance photographs confirmed the existence of multiple Liberty ships under construction simultaneously at individual yards, German planners recognized that their U-boat campaign had become mathematically unwinnable. Admiral Karl Donitz, commander of the U-boat fleet, wrote in his war diary on May 8, 1943, "The Americans are building ships faster than we can sink them. The industrial capacity they have achieved makes continued Atlantic operations futile." Patterson's personal role in this transformation remained largely unknown outside Kaiser's organization. He refused interviews and avoided publicity. His flight logs from this period reveal a man consumed by continuous improvement. Even as his system achieved unprecedented success, Patterson's notes identified areas for refinement. He experimented with different survey altitudes to optimize observation detail. He tested various camera configurations to improve photographic documentation. He developed standardized terminology for describing construction problems so that his verbal reports to supervisors became more precise and actionable. The drive for perfection came at personal cost. Patterson was flying 9 to 12 times daily, accumulating 60 to 70 flight hours per week. His wife Eleanor kept a diary during this period, later donated to the National Archives. Her entries document the physical toll. Robert comes home so exhausted he falls asleep at the dinner table. His hands shake from constant control stick grip. He dreams about ships and wakes up shouting coordinates. But Patterson continued because he understood what was at stake. Every day of construction time he eliminated meant another ship carrying supplies to Britain sooner. Every efficiency improvement meant more ships built with the same resources. Every ship meant more food, more fuel, more weapons crossing the Atlantic. Patterson never flew combat missions, never fired a shot, but his contribution to Allied victory was quantifiable in the thousands of tons of cargo his efficiency improvements enabled. The end of World War II in August 1945 might have ended Patterson's career as an aerial coordinator. Instead, it marked the beginning of his system's expansion into civilian industry. The techniques Patterson had developed for shipyard coordination proved applicable to any large-scale manufacturing operation where spatial relationships and timing sequences determine efficiency. In November 1945, the Ford Motor Company hired Patterson as a consultant for their Willow Run bomber plant conversion to civilian automobile production. The facility, which had produced B-24 Liberators during the war, covered 3.5 million square feet, 67 acres under one roof. Plant managers faced the same coordination challenges Kaiser had encountered in 1942, how to synchronize thousands of workers performing interdependent tasks across vast spaces. Patterson applied his aerial survey principles, though the enclosed factory required modifications. He used catwalks positioned at 60 feet above the production floor, replicating his aerial observation height from the shipyard. He installed a comprehensive photography system that captured the entire assembly line every 30 minutes. Most importantly, he created a central coordination office where shift supervisors could view the entire production process as a synchronized system rather than isolated stations. The results at Willow Run mirrored his shipyard success. Assembly time for civilian automobiles decreased by 38% within 6 months. Quality defects dropped by half as coordination problems were identified and corrected before they propagated through the production line. Worker productivity increased while reported fatigue decreased, the same pattern Patterson had documented at Richmond Shipyard. Patterson's methods spread rapidly through American industry. Boeing adopted aerial coordination for their Seattle aircraft assembly facilities. General Electric implemented similar systems at their turbine manufacturing plants. By 1950, Fortune magazine estimated that 40% of major American manufacturing facilities employed some variation of Patterson's overhead coordination techniques. The article noted that Patterson himself had trained fewer than 30 coordinators personally, but his methods had been studied, adapted, and implemented across virtually every heavy manufacturing sector. The academic recognition came later but proved equally significant. In 1952, the Massachusetts Institute of Technology invited Patterson to deliver a lecture series on industrial coordination. His presentations attracted not just engineers but mathematicians who recognized that Patterson had empirically discovered principles that would later be formalized as systems theory in operations research. Professor Norbert Wiener, founder of cybernetics, attended Patterson's MIT lectures and later wrote that Patterson had intuitively understood feedback control systems years before the mathematical frameworks existed to describe them. Patterson's personal archive, donated to the Smithsonian Institution in 1978, contains correspondence revealing the breadth of his influence. Letters came from shipyard managers in Sweden asking for coordination advice, from automotive executives in Germany requesting consultation, from aerospace engineers in Britain seeking to understand his methods. Patterson answered every letter personally, often with detailed sketches showing how his principles could be adapted to their specific situations. The recognition Patterson valued most came from an unexpected source. In 1958, Dorothy Fletcher, the crane operator whose efficient technique Patterson had identified and promoted in 1942, wrote to him. She had remained at Richmond Shipyard after the war, eventually becoming the yard's first female superintendent. Her letter thanked Patterson for seeing what I was doing when nobody else noticed, and for making me believe I could teach others. Patterson kept Fletcher's letter in his flight jacket pocket for the rest of his life. When interviewers asked about his proudest achievement, he would show them the letter and explain, the ships were important. The system was important. But finding Dorothy Fletcher and making sure her talent wasn't wasted, that's what I'm most proud of. The war would have been won eventually. But Dorothy's contribution might have been lost forever if someone hadn't been watching from above. By 1960, Patterson's coordination innovations had become so integrated into American manufacturing that many practitioners no longer knew their origin. The techniques were simply how things were done, the highest form of success for any innovation. Patterson himself had returned to Alaska, flying bush pilot routes in the territory that had become a state in 1959. He told friends he had grown tired of factories and missed flying over mountains where the only thing he had to coordinate was himself and the weather. The final accounting of Patterson's contribution to World War II can be calculated with remarkable precision. Between September 1942 and August 1945, American shipyards produced 2,710 Liberty ships. Of these, Kaiser's yards built 1,490, 55% of the total despite operating only 30% of American shipbuilding capacity. Richmond Shipyard No. 2, where Patterson's aerial coordination system was first implemented and most thoroughly refined, built 490 Liberty ships with an average construction time of 39 days per vessel. Statistical analysis by the War Shipping Administration compared construction times at yards using Patterson's methods against yards using traditional coordination approaches. The differential averaged 18 days per ship. Multiplying this differential across the 1,490 ships built at Kaiser's yards suggests Patterson's techniques saved approximately 26,820 construction days, equivalent to building an additional 73 Liberty ships using the same resources. Each Liberty ship carried 10,800 tons of cargo. 73 additional ships represented 788,400 tons of additional cargo capacity. This was enough to supply 15 infantry divisions for 3 months, or to deliver the fuel for 4,000 bomber missions, or to transport the food that kept 2 million civilians alive during Britain's darkest supply crisis. The numbers were abstract until translated into lives saved and battles won. The human cost prevented is harder to calculate but no less real. Marine Colonel Howard Graves, who commanded transport operations across the Atlantic in 1943-44, estimated in his post-war memoir that every week of supply delay cost Allied forces approximately 200 casualties from shortages of ammunition, medical supplies, and food. If Patterson's efficiency improvements accelerated supply delivery by the equivalent of 73 ship voyages, and each voyage took an average of 45 days round trip including loading and unloading, then his contribution advanced supply delivery by 3,285 ship days. Translating this into actual calendar time is complex due to varying convoy schedules, but a conservative estimate suggests Patterson's innovations advanced the supply timeline by 4 to 6 weeks across 1943 to 1944. Using Colonel Graves' casualty estimates, this potentially prevented 800 to 1,200 casualties from supply shortages. Patterson never claimed credit for these numbers. When the Smithsonian conducted oral history interviews in 1976, Patterson deflected questions about his strategic impact. "I was just a pilot doing a job. Henry Kaiser built the ships. The workers built the ships. I just flew around and told people what I saw. If that helped, I'm glad. But don't make me out to be some kind of hero." The real heroes were in the Atlantic convoys and on the invasion beaches. Robert Patterson died on February 14, 1982, at age 74, and a small plane crashed near Fairbanks, Alaska, flying supplies to a remote mining camp, the same work he had been doing 40 years earlier when the war began. His obituary in the New York Times ran 4 paragraphs and mentioned his shipyard work in a single sentence. Most readers had never heard of him. The Liberty ship legacy is more visible. As of 2025, 2 Liberty ships remain operational as museum ships, the SS Jeremiah O'Brien in San Francisco and the SS John W. Brown in Baltimore. Both ships carry plaques acknowledging the workers who built them in Kaiser's yards. Neither plaque mentions Robert Patterson or the aerial coordination system that made their rapid construction possible. But in the archives of the Smithsonian's National Air and Space Museum, Patterson's flight logs remain, thousands of pages of handwritten notes recording 3 years of daily observations from 800 feet above Richmond Shipyard. The logs detail a revolution in industrial coordination that helped win a war and transformed how America manufactures everything from ships to automobiles to aircraft. The logs end with Patterson's final entry from August 15, 1945, the day Japan surrendered, last survey flight. 7 building ways empty. No ships to watch. War's over. Time to go home. Final observation, from up here, victory looks like an empty shipyard, which means we built everything they needed, and we built it fast enough. That's all that ever mattered. The mathematics were simple after all. Build ships faster than the enemy can sink them. Coordinate workers better than chaos can scatter them. Watch from above what others miss from the ground. Patterson had solved an impossible problem with an obsolete biplane and a Bush pilot's eye for patterns. The solution had been elegant: just fly in circles and pay attention. In the end, that attention, sustained daily through 1,095 survey flights over 3 years, had helped carry American industrial might across the Atlantic. The ships Patterson helped build faster carried the supplies that sustained Allied armies, fed besieged populations, and fueled the bombers that destroyed Nazi Germany's industrial capacity to continue fighting. One pilot's impossible trick hadn't just made Liberty ships appear every 4 days. It had helped win World War II. Up next, you've got 2 more standout stories right on your screen. If this one hit the mark, you won't want to pass these up. Just click and check them out. And don't forget to subscribe and turn on the notification bell so you don't miss any upload from us.